a bit more detail and do examples of doing inverse Laplace transform. So we have the Laplace transform going from the t to the s, and the question is, we spoke about, is there actually an inverse? The answer is yes. Now there's some technicalities. Now I think I may as well just specify the technicality. I think what happens is it chops off negative time. So you can have a function of t, let's say, I think a good example would be just y equal to 2t, for example. And you can do the Laplace transform, and I think you'll get 2 over s squared. And then, so this is a function of s. And maybe we'll just write down y equal to 2 over s squared. And then when you send back, you don't get exactly 2t, you get 0 on negative times, and then it's equal to 2t. So it's not a perfect inverse is what I'm saying. But if you take, I think t to be, now it might be, it'll either be 0 to infinity or 0 to infinity. It is a perfect inverse, but we don't really need to worry about that because we'll always be interested in positive time anyway. So for us, it's going to have the special property that if you take some function, and we'll write this in various different ways. So if you take some function of t and you find the Laplace transform of it, and say we'll use, doesn't really matter what color we use. So if that's the Laplace transform, except for the kind of technicalities we were talking about above, the inverse Laplace transform sends it back. So another way to write that is, you could say, if you start with a function and do the Laplace transform, and then do the inverse Laplace transform, you get back to where you started. Well, actually, just to kind of show and to do the thing above, actually gets sent back to u of t, which you know from your beams, times f of t. In other words, it's a function that's the same as f if t is positive, but it's actually 0 if t is negative. But that's really, we don't need that. Basically, we're going to, because we're actually going to always just think about positive time only. Right, so there is such a thing, and in terms of us, we've got this table of Laplace transforms. We just run things backwards. Now, first of all, the inverse of a linear transform is linear. So if you're sending back a sum of functions, so this would be your sum of functions, you do it term by term. So first you send back a big F of s, plus then you send back b times g of s, that's term by term, fixing constants. You can fix the constant a and b. The first shift theorem is probably the hardest thing we'll see, and usually we will use a bit of color to show that. How does this work? Well, if you've got something where, so that's the Laplace transform, that's big F, where the s has been shifted to s plus a, that's called a shifting in the s domain. When you send it back as normal, and then you multiply by the what we're calling the exponential shift. Usually I'll do that yellow bit in red. Powers, that's in the tables. 1 over s to the n goes back to t to the n minus 1 divided by n minus 1 factorial. This one we've seen in the previous lecture. And this is all these, this table is in the in your announcements. Okay. Yeah. Right. So I think we're going to do some examples. Loads of examples, actually, is what it says. This is the hardest bit, really, and there's a good bit to it as well. Right, so we'll take our time. So find the inverse Laplace transform of the following functions. So here's the first example. So we'll read the discussion here. There's nothing like this in the tables. If you look in the tables, you will not see this. Now, what you will see, if we even forget about the s, for example, suppose you had just 12 over s plus 3 times s plus 2. And you said, okay, that is, for example, take out the 12. It's 1 over s plus 3 times 1 over s plus 2. And you could say, I know that 1 over s plus a gets sent to e to the minus at. So question mark, could I send this back? Could I fix the 12? And then I said something about, oh, do it term by term. Send back the 1 over s plus 3. Send back the 1 over s plus 2. Isn't that what it is? Question mark. The answer is no. It's not that simple, unfortunately. That does not work. And I mean, the easiest analogy for you is to think about differentiation. Like, is it the case that the derivative of t squared sine t is equal to the derivative of t squared times the derivative of sine? The answer is no. There's a product rule. That's also wrong. So it's a similar story here. There's no reason, if it was like this, the Laplace transform would be called multiplicative, but it's not. Now, what about that term by term? Well, that's linear. That's if the things you're putting in are a sum. If it's a sum, it's no problem, but if they're multiplied together, no good. So this doesn't work. So while you might see the 1 over s plus 3 in the table and the 1 over s plus 2, they're multiplied together. It's no good. You can't do anything with it. You're only good with sums. So what you want to do is you have this complicated thing, this big f of s. You need to write it as a sum of simple things using partial fractions. So the first thing you need to do is, in partial fractions, factorize the bottom here. Thankfully, it's done. So what are we going to do now? Well, let's look at the rules. It's a rule 1 and a rule 1. And if it's all rule 1s, that's happy days, and we can use the cover-up method. So our big f of s, the thing we're trying to send back, we know is equal to some constant over s plus 3 plus some constant over s plus 2. So I'll just put them in for a second. A, B. So this is what partial fractions theory tells us. But because they're both rule 1s, we can just do the cover-up method. So what does the cover-up method do? So for s plus 3, I'll go back to the thing up above in terms of the colors. So for s plus 3, what am I going to do? I'm going to cover up s plus 3. And what am I left with? 12 times s over s plus 2. Okay, and what am I going to substitute in for s? The value of s that makes s plus 3 equal to 0, which is minus 3. Now you only put it into the above the line. You leave the s plus 3. You can't put s minus 3 into the bottom. You'd have division by 0, and that's not what the cover-up method is anyway. Okay, so that's that side of the house. Now, while I have red here, what is the value of s that makes s plus 2 equal to 0 minus 2? So now what we're going to do is we're going to do the cover-up method for s plus 2. So you cover up s plus 2. What are you left with? You're left with 12 times s over s plus 3. And now what we have to do is substitute in those values of s. So minus 3 here, minus 3 here, minus 2 here, minus 2 here. And then let's see what nice numbers we get out. So I get minus 36 divided by minus 1, which is 36. And the other one is minus 24 over 1. So you get this. Now, rather than kind of writing it as 36 times 1 over s plus 3 minus 24 times 1 over s plus 2, we'll just kind of get used to this one. So we'll get used to that the inverse Laplace transform of, say, some constant a over s plus little a, which is the same as the inverse Laplace transform of a times 1 over s plus a, they're the same thing, is equal to the constant a and then the 1 over s plus a using the thing on the, that's 3.9 there, e to the minus at. Okay, and so what I'm saying is that when you have a constant on top, you can just fix it like that. Okay. So this thing is ready to send back. So therefore, little f of t is equal to, so we're just going to fix that 36. And what does 1 over s plus 3 go back to? E to the minus 3t. and fix the minus 24. And what does 1 over s plus 2 get sent back to? E to the minus 2t. And we might just make a little comment that this, you've got two negative exponentials. This one goes to 0 fast. And then relatively, this one goes to 0 slow. So when you've got fast and slow, that's overdamped. Now, not everything we write is actually corresponds to a damped harmonic oscillator, but this one could. Okay, so that's one example done. Let's look at another one. So you look at this, the 4s over 36s squared plus 1. Now it looks like something in there, the first thing is if you try to factorize the bottom, you should really look in the tables first, because you'll see something it looks a bit like s over s squared plus omega squared. But if you did happen to try and factorize it, it looks not a bad idea to try and factorize it. It has no real roots because it's a square plus something positive. It's strictly bigger than 0, so there's no real roots and no real factors. So it does look like something. So the issue is, and we've got an algebra issue here, is the 4 and the 36 are our problem. So let's see how we could possibly deal with that. Right. So the 4 isn't really a big deal because I can just take the 4 out as a constant. I think the way I'm going to handle this is the bigger issue is the 36. So how do you get rid of that 36? So you have 36 times s squared. To undo a multiplication by 36, we need to divide by 36. So we want to multiply above and below by 1 over 36. This is probably the cleverest thing to do. Now, 4 divided by 36 goes in 1/9 times. So you can do 4 over 36 on top. You get 1/9 times s. And then on the bottom, you have 36 s squared by 1 over 36 will give you s squared plus 1 over 36. Okay, so that's pretty good. So you can take out the constant 1/9 if you want. And you've got s over s squared plus 1 over 36. Now some of you might recognize the 1 over 36 because look what you're trying to compare here. You want both of them to be squares, and some of you might notice that 1 over 36 is actually 1/6 squared, but if you don't see it, any positive number can actually be written as a square. Now I'll do it with 7 and then we'll write it more generally. So if you say 7, what you can do is you can do square root of 7 squared, and that works for any positive number at all. So if I write down, let's just say a is equal, now a has to be positive. A is the square root of a squared. So if you couldn't recognize 1 over 36 as 1/6 squared, you're okay because you can do s squared plus square root of 1 over 36 squared. So you're actually okay. Now that's in the right form. It's a constant times, no problem. And we've got the s over the s squared plus omega squared, and the omega, you'll have to be able to see the pattern there, is equal to square root of 1 over 36. So we get the f of t, sending it back. So we're doing the inverse Laplace transform of big F of s, little f of t, fixed to 1/9. And we've got a cos omega, which is 1 over the square root of 1 over 36 times t. Now, if you want, you could possibly put in the that square root into the calculator and get the 1/6 if you want. Now, we were saying a moment ago that not everything is a damped harmonic oscillator. This wouldn't. This would merely be an oscillator, but no damping. Okay, so a spring basically. Okay, happy days. Example 3. Oh, we're going to be nasty on space here. Almighty. Okay, so we look at this, and there's nothing like this in the tables. Now you might have, after a while, we're going to be seeing something a little bit later on, and you might kind of say, oh, I think this might be something like 1 over shifted s plus omega squared. You might say something like this. And if you go down that path, you'll be okay. Okay. Maybe you'll write in the other thing as well. Actually, let me just write this again. Okay, so a little bit down the line, you'll be thinking that, okay, this actually looks maybe a little bit like s plus s squared plus omega squared, and maybe a little bit like omega over s squared plus omega squared, but possibly the s is shifted to s plus a. And actually, if you run that analysis, you will end up doing okay here. Okay, so these in the language, these are shifted cos omega t sine omega t, where the s is shifted to s plus a. As I said, if you actually try and do that using the techniques later on, you're going to find that omega is equal to 0 and a is equal to 1. But that's just kind of looking a bit further ahead. But what you should probably do first is, okay, let's just do partial fractions. So the first thing is you factorize the bottom. So let us look at that. So we've got s squared plus 2s plus 1, and we'll factorize this using the AC method, or you can use whatever you want as long as you're getting it right. So the AC method says a by c, 1 by 1 is 1. We look at the factors of 1, all you get is 1 and 1. And you can take a pair of those, 1 and 1, and get plus 2s. So we get s squared, and then the 2s there is equal to 1s, which is s, plus 1s, which is s, plus 1. And now you have a common factor out of the first two is s, and you're left with s plus 1. And then if you want to get s plus 1 again, all you can really take out is s plus 1. And now you've got a common factor again. So you can take out that common factor of s plus 1. And what are you left with? So it's s plus 1 by s plus 1. Now, this is a rule 2 because s plus 1 is repeated. Now, we're in a bit of bother with space here. So it's rule 2. So as I said, we're okay. So each of these factors associated term. So we've got 2s plus 6 divided by s plus 1 squared. 2s plus 6. What we got? Okay, so the rule 2, if you go back and look at it, now what you'd be tempted to do is okay, I've got s plus 1 is the first factor, s plus 1 is the second factor, and just do two constants there, a and b. That's what you'd be tempted to do. But unfortunately, that doesn't work because you actually only have, the thing on the right is it's just a plus b over s plus 1. It's just a constant over s plus 1. It doesn't do the job. So what rule 2 says, you change it by squaring this, similar to stuff in chapter 2 as well. So the crack here is you want this to equal this. Now, this is where I think it's good to slowly write this as a single fraction and compare. So what you want to do is the sum of fractions on the right hand side, you want to write this as a single fraction with the same denominator. That's important. With same, well, denominators, fancy word like bottom on the left. Okay, so the b over s plus 1 squared is fine, but I need the a over s plus 1 to have the same. So what I can do with the a over s plus 1 is I can multiply it above and below by s plus 1. And that red thing is itself equal to 1. And so multiplying by 1, it looks different, but it's the same number. So we have a Now you can do this a bit quicker if you want, but I'm just showing you exactly how it works. So that's the first fraction, multiplying above and below, plus the second fraction. And we have a common denominator now, and so we've got a times s plus 1 plus b divided by s plus 1 squared. Now if we compare, we'll note that the bottoms are the same. So if we want these two things to be equal, we need the tops to be the same. So we want 2s plus 1 equal to this. Now, if you go back a bit, there's a further remark to do this a slightly easier way, but for the moment, we'll try and do it the same all the time. So we're trying to say that these two things are equal. So you can put in values of s to generate equations. Now, the cleverest value to put in initially is -1 into the blue bits, because that will kill the a. And if you do that, you'll get 2 times -1 plus 6 equal to a times 0, which is 0, plus b. So we very, very quickly found that b is equal to 6 minus 2 is equal to 4. Now you put in the next easiest value of s, which is probably 0. And the blue bit on the left-hand side, the 2s plus 6, would be 2 times 0 plus 6, which is 0 plus 6, which is 6, equal to a times 0 plus 1 plus b, but we know already that b is equal to 4. So we've got 6 is equal to a plus 4, and take away the 4 from both sides, a is equal to 2. So what we have is the thing that we started with. Has it got a name? X of s is equal to a, which is 2 over s plus 1, plus b, which is 4 over s plus 1 squared. Right. So, yeah, so this is what we're looking at. Now we want to send this back. Now what we can say is the first term is going to be no problem, because 2 over s plus 1 is just kind of going overkill here, is 2 times 1 over s plus 1, and that gets sent back. That's no problem. Inverse Laplace transform, 2 times e to the minus 1t, which is just 2 times e to the minus t. That's no problem. But what about the other term? Okay, so the 4 over the s plus 1 squared it looks like, the thing it looks most like is actually 1 over s squared. The 4 isn't really a problem, and the s has been shifted. So what this actually is, the 4 over s plus 1 squared, the 4 don't worry about, is a shifted, I can write 4 here, 4 over s squared. So what's the shifting about? Instead of s, you have s plus 1. Okay, and then we can use the first shift theorem. So we've written it's just repeating it there, really. Now maybe what we'll do is we'll write a little bit down here. So maybe we'll see what does 4 over s squared, what happens with 4 over s squared. It might be worth talking about. So 4 over s squared, which is 4 times 1 over s squared, the inverse Laplace transform of that, you can fix the 4. And what about the 1 over s squared? We'll use the formula down the bottom. It'll go to t to the power of 2 minus 1 over 2 minus 1 factorial. The 2 minus 1 is 1. 1 factorial is 1. Divided by 1 doesn't do anything, so it's just 4t. So all I want you to note here is that 4 over s squared goes back to 4t. That's what we're going to see. Yeah. So I think we're going to go back to x of s on the next page. Yeah, we've done this. Okay. So Yeah, there's a lot of writing done here. So we go back to our x of s. What was our x of s? 2 over s plus 1. So the way I'm going to write the 4 over s plus 1 squared is like that. So it's a shifted 4 over s squared. And what does the first shift theorem say? It says if you're, so run this the other way around, if you have a shifting in the s domain, it turns out to be multiplication by an exponential in the t domain. And look, you just send back the big F of s as if nothing was going on. Look, it's not easy. There's no, I can't make it. It is as hard as it is. Okay. So anyway, this will go back to. So the first term is fine. It's 2 times e to the minus t. We've seen that already. And then, so this shifted 4 over s squared. What does the first shift theorem says? It says it goes back as normal, but multiplied by an exponential shift. And if it's plus a, it's e to the minus at. Here, like that. So we'll try and put in some, it's not easy, there's no two ways about it. So this is the f of s, and we'll put in a plus 2 there eventually. And this is the f of t, and we'll put in the exponential shift. This is plus 1, e to the minus 1t. So this is what the first shift theorem says, and I should put a little. Yeah. So if you have something that's shifted, instead of s, say you have s plus 1, you bring it back as normal as if it wasn't shifted. So that's the 4 over s squared. Bring that back as normal to 4t. But then you account for the red shifting from s to s plus 1 by multiplying by e to the minus t. Yeah, I can't say that it's easy or anything like it. That's a critically damped, correspond to a critically damped oscillator because the speeds are the same. Okay, we'll pause and upload this one.